I'm James. I'm a PhD student from the University of Bristol. I'm studying energy, essentially. So I'm looking at software, how we can change our software to change the amount of energy to hopefully prolong our battery life a bit longer. So I'm going to talk to you a bit about how we can measure our energy, how we can reduce it, and I'm going to talk to you a bit, give you a bit of introduction about where energy comes from and why our processes dig in. So there's going to be a bit of physics involved, but hopefully not too much. So what's it all about? In the end, we've created a board which looks a bit like this, and this is one of our energy measurement boards. We plug this into lots of other different devices, and this spits out a power trace of what power it's using at what instant in time. This is one of the very first versions. We're now 3 or 4 versions further than this, and we've got much faster than this. So I'm going to talk to you a bit about how this works, but first I'm going to have a quick recap so that you understand everything I'm saying. So resistors. If you're here for the previous talk, you know all about resistors and capacitors. The analogy is that this, if it was water flowing through a pipe, this resists the flow. So it affects the power that your resistor will dissipate. High resistance dissipates higher power. And then you've got your V equals I times R at the bottom to calculate the voltage. The other important component is a capacitor. This is analogous to a bucket which will store electrons and then allow you to tap it off at a further point. Electrons get stored in this capacitance and then they'll be available for use further on. So this it takes energy to charge up the capacitor as opposed to the resistor, which affects the power. So we have this interesting concept of what is energy. Energy is, roughly speaking, the number of electrons. So if you've got a high amount of energy stored in your battery, you've got a lot of charge, you've got a lot of electrons stored in there. That's not strictly true, but it's a good way of thinking about it. And the amount of energy taken to do something. So, for example, charging a capacitor takes a certain amount of energy. Doing some complex calculation on your processor, on your Arduino, that takes a certain amount of energy. So, units. Most people get confused. People say, oh, my battery power is low, but they actually mean the energy in your battery is low. Power is strictly how fast you can get that energy. So if you have a high-powered battery, that means you can discharge the battery very, very fast. It doesn't mean that it'll last for a long time. High-powered battery will probably last for a very short amount of time, actually, since all of the energy will be gone much quicker. Energy is actually how much work you can do on it. So it's the total amount of charge stored in your battery. So for example, if you have a laptop charger rated for 65 watts, that's 65 joules per second. So that will put 65 joules into your battery per second. And that should be enough background information for this. So what I'm going to talk about in the rest of this, where does energy consumption come from? I'm going to talk a bit about transistors, why they take energy when they switch, why they take energy just when they're turned on. I'm going to talk about how this affects your logic gates, so then build it up to processors and then your entire PCB, your entire system. I'm also going to talk about how we measure this energy consumption. So the board that you saw at the beginning, that I'll talk about how that works, how you can design your own. All of the designs are actually on GitHub, so you can download them and change them. And then I'm going to talk very briefly about how we can minimise our energy consumption. So the levels of energy consumption. At the most basic level, we've got a small transistor. A small transistor will take a certain amount of power and take a certain amount of energy to switch. So building on these, I'll go through that a bit, and then I'm going to build up to Gates architecture of the system. but each of these levels take more energy, more power, and they each get bigger, form more complex systems. So at the very lowest level, a transistor's energy consumption comes partially from its resistor component, partially from its capacitive component, and partially because occasionally it short circuits. And that's normal. During normal operation, you'll get short circuit currents. I'll talk to you about that a bit more. That covers the two components of energy, the leakage and the dynamic. So onto transistor. So if you've been at the previous talk, you'll see that this is a slightly different diagram to the transistors you've seen there. This is a different type of transistor. It's a MOSFET, CMOS transistor, instead of the bipolar junction transistor, which we saw before. This works in pretty much the same way. It's a switch. If you apply a voltage to the gate, then you can current will flow from drain to source. And then this view on the side here is how you'd actually see it if it was on a silicon wafer. So this is a side view of the silicon wafer. In here, this is a tiny transistor. You put the voltage in here, this forms a channel here and allows electrons to flow between these 2 points. And this is quite important when you actually consider why these consume energy. And they consume energy because these red areas between different regions of the transistor cause capacitance between these different doped regions of the transistor. And to charge up these regions of capacitance, you need to put in a certain amount of energy. So each time you activate this transistor, you've got to charge up these areas of capacitance, or you've got to drain them of the charge that they've already got. And this takes a certain amount of energy and takes a certain amount of time. Similarly, you get the resistance effect. If your transistor's on, you're having current flow from one side of it to the other. That's going to be resisted by the just innate resistance of the silicon. So this might be very small, but when you add it up, it takes a significant amount of power. That is the leakage power. It's called leakage. That's just when it's on. It's when the transistor's not doing anything. It'll just take a certain amount of power. If you left the transistor on for a long time, it takes a certain amount of energy. And then finally, the short circuit current. Short circuit current. So that only appears when you have multiple transistors combined together. So this is very simple NOT gate. If you put if you put a voltage on the in, it will put a 0 on the out. If you put 0 on the in, it will put a 1 on the out. And that's because this top transistor is an inverted form of the bottom, but it will turn on if you put a 0 on it and a 1 if you put it as 1 on it. The way around, sorry. But because you get different transistors here, you get slightly different switching time. And in certain circumstances, you'll get a time when both of these transistors are on and current flows directly from positive to ground, causing a very short but large spike in power dissipation. And this is normal and can't normally be avoided, but it's worth considering as a source of power and energy consumption. So that's a very quick look at how transistors actually consume energy. At the next level, you take it up a level of abstraction. That's my NOT gate again. This is each going to be connected to other gates. So each NOT gate or each NAND or whatever type of gate you're using will connect to other transistors, other gates, and because of that capacitance you've got on each transistor, you've got to charge up each time you flip. So each time you flip, you're charging up the line between one end of the gate and the source of the other gate. That takes a certain amount of power, it takes a certain amount of energy as well, and that causes more energy consumption. So each time you flip costs you a certain amount of energy. You can see this more when we have a more complete circuit. So if I was to flip the A line, this also toggles this intermediate line and the S output. So by toggling this one line, I get 3 lots of energy consumption. It's not quite that simple, but it's a rough guide on the more complex the circuit, the more internal flips you're going to get, the total amount of energy is going to be larger when you flip one line. And if we add to this and flip line B, you see that this is now turned off these two that were on before and turned on these two down here, along with B line. That means that from going from A1 to A and B being 1, it's flipped a total of 5 lines. So one point I'm trying to make is that these interactions are immensely complex. The sources of energy consumption are very, very difficult to understand at the most basic level. When you put it together into a huge circuit, a huge processor, it becomes very, very difficult to analyse in this kind of depth. So the consequence of each bit flipping having a energy consumption means that if you clock it faster, all of your bits are going to flip faster. And then this means you get a faster rate of flips per second, and then you get higher power. So your higher rate of energy being consumed per second equals higher power. So that's one of the reasons that why when you clock your processor up, you see a higher power usage. And onto another abstraction level, processors. So this is quite far removed from the basic transistors and basic gate level. Consider the pipeline processor here. Each stage in this pipeline, each instruction is going to take a slightly different amount of energy. For example, having an add instruction is fairly simple, whereas a multiply instruction triggers a huge cascade of bit flips and takes a significant amount more energy to compute rather than a simple add. If we go even further up, you see we've now got a system, and if you consider here, we're so far away from the transistor level of each transistor having a certain resistance and capacitance that it's very, very difficult to model on that level. So for example, one way of thinking about this is I've got a SPI hardware block. I can do one communication with that, and it will take me X amount of joules. And one way of budgeting your energy is by considering your hardware blocks like that. You could do one memory access that will take you a certain amount of energy. You could do some operation for a certain amount of time, and it takes you an average amount of power. So accessing the hardware costs energy, outputting pins costs energy. So that's a quick overview of where energy comes from at each level. But because it's so complex, we don't try and derive it from that theory, we measure it instead. So we will do some empirical measurements and try to assign to each hardware block, say, I2C block, this operation takes this amount. If I want to send 8 bits of data, it's going to take X amount of joules. If I want to receive some, it's going to take Y amount of joules. And then we can minimize our energy by saying, oh, we don't need to do this access, we could cut that out. Our energy is going to go down by this amount. So we measure it. This is a second generation board. You saw the first one. This one's got a high-speed ADC in the middle here, and some other amplifiers here which you can't see in the wires. This was then developed a bit further into this system we've got on here. This has been used for a couple of projects that we've got running with Embecosm and the University of Bristol. This board here is the main energy measure bit. It sits on top of another ARM processor which does stuff like trace collection, compression, sends it back over the USB so you get your power trace, you can then visualize it, and then you can correlate that with bits of your application. For example, if the first bit of your application is doing some communication over the serial, you can say it uses that amount of energy. If it then does some processing, you might see a spike in power consumption where it starts using the CPU more intensively. So this little device allows you to do that. I'm going to talk to you a bit more about how it actually works. So the way we measure power is we put a very, very small shunt resistor in line with what we're trying to measure. So if we're measuring a processor, we put this shunt resistor in line with the processor, between the power supply and the processor. And then we've got a power monitor, which is our block, as you saw in the previous slide. This power monitor is the PCB sitting on top here. And then the logger, which is the board underneath. And each time you measure the voltage drop across that resistor, you can calculate the current going from the resistor from Ohm's law. You can then measure the voltage at one side of the resistor and use your previously calculated current and the voltage you just measured to get your instantaneous power. So if you then do that lots of times, you'll get some sort of power trace. So let's have a close look at this power monitor. It's a fairly simple design. It's just an amplifier and an ADC. And this ADC spits out 12 bits of data and is sent on to the logger. So if your voltage drop across your shunt resistor is looking something like that, your amplifier will then amplify it, take away the common mode so that it can be properly converted by the ADC, and then the ADC will quantize it and you'll get a certain number of bits back, each representing how much power is being used, how much power is being dropped across that resistor. Then that gives you a power trace, which you can look at in GTK wave. So this was taken yesterday when I was playing with an Arduino. It's on when it's flashing an LED and it's off when the LED is off. So this was flashing fairly slowly, but you can see the power draw goes up significantly when you've got the LED turned on. And that's because the LED takes about 30 milliamps. So from this power trace that you've got here, you've got this certain curve power at each time. You can then integrate that to get the energy. So if you take the area between each, you eventually get something that looks like that, and that gives you the total amount of energy which is being consumed in that time. So if you had a program and you were doing one certain thing at the beginning, you could say, start my power trace over here, end it here, how much energy have I used in that period? I've used that amount of energy. So this allows us to, if we've got one application which is going to do one thing, it's going to process one image and then send it across the web. You can say, here it's taken this amount of energy. So we've been attaching these probes to lots of different boards, and one trick we've found is this switch mode regulator is on lots of high-end boards. So the Beaglebone has got some regulators which look like this, and these regulators work differently and work via feedback. So they've got a feedback line which allows them to alter their output voltage to make sure it's smooth and consistent. But this also means that we can trick the regulator essentially, put our shunt resistor in between here, between the feedback and the output. This means that when it sees the feedback, it will compensate thinking, oh, the voltage has dropped too low, we should output some higher voltage. And then that means your target processor's got a nice smooth voltage. You'll never dip below what it's expected because of the resistor you've just put in that circuit. And just generally makes things a lot easier to handle. So we did this with the Beaglebone. See a horribly hacked apart Beaglebone here, where we've taken off 3 different measurement points and stuck some wires on with some, and these wires go off to our energy board with an inductor and the shunt resistor on there. So this is quite useful because this allows us to measure the processor's energy consumption, the hardware peripherals, and the memory. So it allows us to break it down into those 3 different categories. So this is not the only way of measuring power consumption, measuring energy. But it's the most applicable one for embedded systems. So if you're doing some home automation stuff with just doing smart meters, then use a current sensor like this, which you just stick around the wire. It measures the changing magnetic field, but it requires alternating current, which most embedded systems don't use. If you're doing silicon design, quite often they've got a very high-spec thermal camera, which they can put onto the chip, and then that'll give you the hotspots of which areas are being used most frequently in the chip, and you can then go back and optimize your silicon design by saying, oh, this area of the chip's getting really hot, what can we do to minimize the power consumption in that area? So that's measuring. Next, we'll go on to reducing energy. So this is partially based around my own research, partially based around just what we've seen happening. Changing clock frequencies and voltage. Is it better to run hot and fast or cool and slow? A lot of the time it depends on what you're doing. So for example, you have less leakage, your transistors are on for less time if you just run it very, very quickly. However, your peak power dissipation spikes up, so your chip gets very, very hot. If you use less memory, memory accesses are bad. For example, given the bugle bone, all of the memory is stored off chip. So accessing that main memory means that you have to go off the chip, you have to go along the PCB, go into the DDR memory, and then return all of that access back, and it takes a huge amount of energy to go out onto the PCB like that. The third point, use the hardware available to you. So don't bit bang. If you've got a serial block available, use the serial block. If you've got I2C, rather than using the library which implements the software, use the hardware block. It's designed for that purpose, it's much more efficient. And finally, if you can, go to sleep and put the processor into its most low power mode you can, and then only wake up when you actually need to do something. Polling is bad. So on to another thing about the higher clock frequencies. Give the higher power because it's faster bit flipping, and then you still got to charge up the same amount of capacitance. Shorter execution time also means that your leakage is lower, so that resistance that we saw from one side of the transistor to the other, power is going constantly through that. If you have a shorter time, you get a waste less energy. However, if you do this too much, you get too hot. And there's an odd feedback effect, which means that the hotter you get, the more resistance you get in your transistor, which makes the leakage higher, which makes more heat, which makes more current, which makes more power, which makes more heat, which essentially results in that. So, I'm sure you've seen that happen before. So yeah, there's a limit, which is why we don't all run really fast and why we're hitting that ceiling of about 3 or 4 gigahertz in our top-end processors. Onto memory. It's expensive to access memory. If you look at this memory hierarchy here, if you do a cache miss in every single layer, you're going from the processor to L1 to L2 to L3, then finally to main memory. Costs really a lot, but yeah, you might be thinking, oh, this is just a modern processor, it doesn't matter for embedded stuff. But it does. This is on a very, very small Cortex M0. It's still 50% more power to do loads from memory than it is just to do some computation. Right, so in conclusion, it starts with the transistors. I've given you a quick overview of how the transistors consume energy, how power is affected by all of this. In general, that's a bit too low level to actually think about. So because of this, measure the energy. Go and build one of those hardware measurement boards, or come to the workshop tomorrow, we'll pick you up and will measure some of the power that your project is dissipating. Run fast, try not to test memory. Thanks. Any questions?
Your measurement kit, are you actually offering that for people to use, or can get the boards and what's the setup?
We don't currently have enough to be able to give them out, but all the designs are on GitHub. There's all the software to use them is on GitHub as well. So and most of the stuff we've been able to use open source tools already. For example, the power can be viewed in GTK way quite easily. All of the designs for this most current board here. The designs for this board are all on GitHub. This board at the bottom is just a £10 board that you can buy from ST or anywhere really. And then it just slots on top. You can hook in your other things via these ports here. Google shunt resistors, everything.
Just get back to the specification thing, which said things like what the this one? Oh, there we are. Yeah. So yeah. So 7,000 samples. So that's quite.
It's quite speedy. You can burst up to 6 million samples per second, but because the management board we've got at the bottom, the logger, has only got high speed USB, not full speed. We can't send it. So you can do bursts of 6 billion samples per second and store that in memory, then transfer it.
What voltage drop have you got across that shunt?
So I did have a slide about that. Yeah, so the ADC has a 3-volt reference voltage. So choosing the shunt is important, and we typically go for a voltage drop of less than 50 milliamps, and then there's a high side current amplifier which amplifies up to 2.5 volts maximum, and then the ADC works on a similar range.
Sorry. What's the voltage drop on the shunt?
50 millivolts.
50 millivolts. Sorry, okay.
Yep, thanks.
I was interested on the hardware side again. I was interested in how you approach the challenges of, particularly at 12 bits resolution, dealing with common mode projection ratio and challenges like that. Because even on some of the dedicated silicon for doing this, it's difficult when you're trying to deal with such low power systems and observing with a minimal voltage drop, and you've got effects of switching regulators in there as well.
Yeah.
Is that a journey you've been on?
It's challenging. There are high side differential current amplifiers that we use, specifically designed for this job of working with high common modes and amplifying such small voltage drops. They can be quite noisy, but currently, because we can take 6 million samples per second but can't send 6 million samples per second, we take several samples, average them out, and then send that sample. So we do averaging as well, and that seems to give us a fairly good result, which is consistent. I think we're getting what we expect.
I'm just wondering how your like hardware and software. Let me throw it. So say I've written a bit of software for my PIC in MP Lab.
Yeah.
How would I use your software to match the energy consumption to the bit of code I've written? So if I write an SPI bit of script to query an ABC or something, how do I work out what that spike there was related to that bit of code?
You're going to have to do it by toggling a pin and then interfacing that with the the logger board. So we haven't got the functionality for it yet, but the plan is to have a set of pins on here which you can then trigger via your board under test, and then you can map that back to where it wasn't code. So you trigger this pin, you see that in the trace, you should you can get GTK wave to say an event happened here, and then you can plot that on the power trace as well. You can see that you can correlate that spike back to your application.
So you need to plant milestones in your code essentially.
Yeah, it's
Which philosophy is
Well, it depends how you plant them. But
but hopefully not too much power.
Only what you measure again.
What kind of total dynamic range are you talking about for measurements? So if I've got a board, for example, that is in deep sleep most of the time, pulling kind of a few microamps, and then bursts up to say 20 odd milliamps, do you have sufficient dynamic range?
It's challenging, but we can just about get that range. It depends on the shunt resistor that you choose. Higher value shunt resistors mean you can get more range, well, get a certain range, but then you get a larger voltage drop. Currently, with the board we've got here, we can measure down to about a 10 microamp resolution, and then that goes up to about 50 milliamps.
That sounds perfect for my project, so
I'm guessing most of the time you don't actually need that high dynamic range, because if it's right down at microamps,
yeah.
then the total amount of energy consumed for however long,
Yeah,
you can measure that separately.
I mean, the main concern when you're building these kind of things is to make sure that the damn thing's asleep when it's supposed to be asleep.
Yeah, I mean certainly, and when you get onto certain things like the Beagle though, speed is a very good proxy for power consumption. Certainly for a first approximation. I mean, it's very nice to have a fancy power meter, but seeing how much idle your processor is will pretty much tell you how much power it's using. And certainly in terms of, is my new code going to be more or less power efficient? Well, does it run faster? If it runs faster, it's going to lose less power.
There's some interesting research that James has done, which is what this was developed for, which is about measuring exactly that.
Yeah.
And the broad thing is, speed and energy are correlated. But you do find interesting things like on the high-end ARM processors, doing multiplication in the Neon coprocessor is actually energy efficient. So you don't do it for speed, you do it for energy or flow, which is why when you go up to high optimization levels in GCC, when you start getting the coprocessor pulled in, your energy consumption goes down because it's doing its multiplication in the vector coprocessor. And so there are some odd effects.
Yeah.
It's not necessarily true. There is up to a 50% change depending on what instructions you use, how often you access memory, that kind of thing. So it's not an instant amount, but in general, if you want...
But then, if you
to
access
utilize
memory a
straight
lot,
lines.
your memory is generally much slower than cache anyway, so...
I guess so, but yeah, for stuff like the Beagle Bone,
Certainly if you're on level picture, then
yeah.